thermodynamics of a few particle systems under minimal assumptions, or whatever you want.
Good afternoon, everyone. Hope you had a good lunch. So we are going to restart now with the afternoon session. First one will be Ale. So it's my pleasure to briefly introduce him because he has some slides to introduce himself, so made my job easier. But yeah, so he's currently a postdoc in DTU in Denmark and famous for a few things, in particular for having the best Maxwell's demons in the literature. So thank you, Ale.
Thanks for the introduction. Hello, everyone. First of all, I'd like to say thank you for the organizers. It's very nice to be here and also very nice to be invited to give lectures on a topic that I really like, especially when you are a young researcher. And it's my first time giving a lecture, especially for a big audience, and I have some disclaimers. The first one is that I try to make as simple as I can. So this means that I will try to go very slow and I will try to interact. And I also hope that you give some feedback afterwards. My idea is to not use the 1 hour and a half and maybe stay here. And then if some of you would like to come and interact with me, I would be very happy to discuss more of those things that I will be mentioning today. And since it's my first time, of course, that I'm pretty anxious, slightly nervous, so I will start to introduce myself, which I must confess that I think it's a bit cringy to do so, but I was like, why not? So basically, my name is Alexssandre, or Ale, or Alex. I'm Brazilian, and I'm from 2,000 kilometers away from Natal, from this very nice town called Poços de Caldas. And Poços de Caldas is very famous for many different things, especially the food, but also because of the landscapes. Like, we have very nice mountains, waterfalls, and if you like climbing, it's perfect because you have those volcanic rocks here, very nice to grip. And the reason why we have those volcanic rocks, according to my mother, is that Poços de Caldas is at the top of an extinct volcano. Once I searched, apparently it's not true, but it's nice to say this in presentations. So yes, so I was born in Poços de Caldas, a small town for Brazilian standards, a large town for European standards. And then I went to Bauru to do my bachelor. So I tried to find a very nice picture of Bauru, but unfortunately, sorry, Felipe, Bauru is very ugly. There are no nice pictures. However, I decided to put the symbol of the city, which is this very nice sandwich here, which is called Bauru. So there I had my first scientific experience. I started working with superconductivity. It was really nice. I got a grant to do those things. At some extent, it was my first contact with thermodynamics, more from the condensed matter perspective. But then, so when I arrived there, a nice fact was that when I started doing my bachelor, Philip had just arrived, I think, maybe 1-2 years, and I really wanted to do my master's with him, but then he said no and said, look, you should go to Unicamp. And this is what I did. I went to Unicamp, which is in Campinas. This is the campus. The campus is nice, but the picture is bad. And there I started working with open quantum system, quantum thermodynamics. Again, a different way of looking at thermodynamics. I was mainly looking at this perspective of open quantum systems that I will roughly mention today and also in my last class. And then when I was finishing my master's, I wanted to go abroad to try to learn some English, to try to learn more recent things that people are doing in quantum thermo. And then I end up in Krakow, in Poland. So this is the university that I studied at Jagiellonian University. And there I was very lucky because I was in the group of Karol Rzeczkowski and Kamil Korzekwa. And basically it was really nice because when I arrived there, quantum thermal was very hot, and people were trying to tackle questions that I will pose in a bit in a model-independent way. What does that mean? It means that, well, you use minimal assumptions to describe the thermodynamic of systems which are very far from equilibrium. And you don't need to solve equations of motions to do this. So this is a bit of a spoiler that I will mention. So I spent 3.5 years there. I defended my PhD, and then many of the things that I will talk today, it's here in my PhD thesis that you can access in this archive address over here. It's some sort like of a book / thesis. And yeah, so if you want to go through details about the things that I will talk today, it's better to take a look at the thesis. There I will not be sloppy and things will be very concrete there. And then when I was finishing my PhD, I was like, okay, it's been 3.5 years that I've been doing quantum thermodynamics, and basically I was in a group which was doing mainly mathematics, and then I was like, maybe I would like to go for another adventure and try something else, something more ground to earth, something where I can do theory for experiments, and this led me to go to Denmark, where I basically now I'm based in Denmark. It's been 2 years, and there I kind of divide my time in 2 different facets of physics. So with Jonathan, we still look at quantum thermodynamics, but now we would like to do something which really has some implication for applications, not something abstract, like to try to develop tools that people can use. And one of the things that I might mention in the last lecture is like look at thermodynamic process as witnesses of quantum properties. What do I mean by this? I mean the following. Imagine that you have a thermodynamic process, and the main agent of this thermodynamic process is this unknown state that you would like to probe. Just by looking at the statistics of your experiment, the ones that you have access, such as, let's say, the heat exchange in the process or the work, can you say something about the nature of your quantum system, such as that the system is entangled, or that the system has non-stabilizerness, or any other quantum property? And can we make this in an experimentally friendly way? Well, I will say yes. Other people will disagree with me. And then maybe on the last lecture, I can convince you that you can use this framework that I will present to derive things which has some nice implications. Well, as I said, so basically I solved part of my problem, which was like, okay, I would like to do something more ground to the earth. We start looking at this type of quantum thermodynamics frameworks to probe quantum correlations. But then part of my time is also dedicated to a different area of physics, completely different one, which is guaranteeing the privacy of quantum networks. And this I have been doing with Ulrich. He'll be here next week, and I will also have a talk next week, which has nothing to do with quantum thermodynamics, and it has to do with this Gaussian ghost here. So basically, I replace Maxwell's demon by Gaussian ghost. Good. And then this brings me to today's lecture. What about today? What I would like to tell you a little bit, and then the way that I will try to proceed is in a way that I will try to do everything in the blackboard. Many people complain that my handwriting is very small, and I think it is indeed, and I will try to do as big as I can, okay? And if you cannot see, just let me know, and then I will try to increase the font, okay? And before I formally start, if you have any questions, comments, or if you disagree with me, please, let's try to have an interactive class. Feel welcome to just raise your hand, or afterwards came to me and say, hey, I didn't understand this part, can we discuss, and so on. I will try to use both. Yeah. Okay. So now I will close my laptop, and then I would like to start. Okay, maybe I will not close the laptop. Yeah. Yes. Yes. Okay. So I would like to start then these lectures in a very informal and another disclaimer, sloppy way. So basically, I know that many of you come from different fields, have different backgrounds. So I would like to try to spend, let's say, 5 up to 10 minutes trying to tell what is quantum thermal. And this is really hard. This is really hard to define. I have my own definitions for this, but it might be that since the field is so broad, other people can disagree with my view of the field. But I will do this in a way that I will slightly introduce what I would like to discuss today, which is this idea of resource theories of thermodynamics. Then I will start with this question here, which for now it will be our main point, which is, do we really need to solve equation of motions to learn something about our system? And the spoiler is that no, in fact, no. We just need minimal assumptions and we can derive many cool stuff. Okay, so let me start then with the slop intro to quantum thermodynamics. First, the way that I see quantum thermodynamics, it is as a theory that you try to understand how quantum features, such as coherence, entanglement, affect classical formulations of thermodynamics. Or better, you look at systems which are very far from thermal equilibrium, such as systems composed of few particles or process which is not done quasi-statically, and try to ask whether you can still do some thermodynamic theory for these systems. And I must confess that this question was already asked and rephrased by many different fields than not only quantum thermodynamics. For example, if you try to describe systems which are far from thermodynamic equilibrium, or let's say that you try to describe quantum systems, and you try to talk about, for instance, entropy production, and those things, there's beautiful results back to the 60s, 70s from people from open quantum systems. If you try to talk about quantum heat engines, meaning that now you take your work medium and replace by a quantum system, many of those theories was already developed in 1959. So those questions are very old, and because of this, they were explored from many different perspectives. Also, I must say that people from condensed matter also cared about thermodynamic properties of systems which are far from equilibrium, right? So, for instance, if we try to do statistical mechanics far from equilibrium, there are many beautiful results, such as fluctuation dissipation theorems, which dates back to 1900, and so on, so forth. So then there was a big boom around 2000, where people start looking at those questions more seriously, and basically they were trying to answer the following bigger question, which is, imagine that we have a thermodynamic system. It's basically composed of infinite particles. You assume that processes are very, very slow, but then you can ask, what happens now if I replace this infinite amount of particles by a few particles? How can I write a mathematical framework for this, which allows me to access those thermodynamic quantities that before I had? Well, but then you can say, but does it make sense to define what is work, heat, if you are far from this? It kind of does, because basically what you can do is the following. Look, now those macroscopic variables, they will suffer a lot of fluctuations. Like, since you are far from thermodynamic equilibrium, there are a lot of fluctuations, but you can still treat them as random variables with certain probability distribution describing those quantities, such as work, heat, and so on. But then what is the most interesting is that those probability distributions, they will not be arbitrarily ones. And this was discovered by the 90s. They must satisfy certain theorems called symmetric theorems, or more popular known as fluctuation theorems. And this was very, very nice. Well, another variant of this question is when we say, okay, so let's keep a bunch of particles, many particles, but now what we do is that we look at finite time process. Because the thermodynamics that we know from the textbooks, there's not so much dynamics, right? It's very, very, very slow things. But what happens if you have some, I don't know, you have a chamber, there's some gas there, there's a piston, and then you push this piston with constant velocity. And then new theories were developed for this. And people, when they were doing this, what they were looking at was specific models and doing theory for those specific models. So basically, what they were doing at the end of the day is solving equations of motions. Okay? As I said, my first disclaimer, this part was very sloppy. I jumped and I was not so coherent. Now I try to bring some coherence. What do I mean by solving equations of motion? So let's take a paradigmatic model in quantum mechanics. For example, an atom interacting with a quantized electromagnetic field. For instance, an atom in a cavity whose interaction is described by James Cummings' model. So let's imagine that we have our atom here. So yes, I have to write big. This is a big atom. This is my cavity. And then they interact according to certain Hamiltonian that I write it in the rotating wave approximation. I know that some quantum opticists, they don't like so much about rotating wave approximation, but for this talk, I will assume that it's perfect and it's wonderful. So let's assume that the interaction here, so not the interaction, but let's assume that, well, my atom is described by some Hamiltonian like this. The cavity is described by some Hamiltonian like this. And then I have some interaction like this. Oops, no. Okay, nice. So basically, this is the local Hamiltonian of our atom. This is the quantized electromagnetic field, creation operator, annihilation operator, and they interact. There's some coupling between them, which is this G. And basically, this interaction is special for the discussion that I will bring. It's an energy-preserving interaction. What does that mean? It means that, well, if the cavity gets an excitation, the atom will lose, and vice versa. Nice. So let's assume that we're interested in the behavior of this atom. And why? Why not? Let's assume that you would like to prepare this state for something, for some nice information theoretic task. And let's look at, for instance, we are interested in the state of the atom. We could, in principle, assume that this is some sort of environment for this atom. It could be that this guy is prepared in a thermal state. Doesn't need to be, but we could assume this. And then, as I said, we are interested in the behavior of this atom. More precisely, in the set of states that this atom can achieve under this interaction. Okay, so I will look at a specific cross-section of the Bloch ball. So let's say here I have, here I have 1, here I have 0, here I have plus, and let's say that the atom starts here. And then the question is like, suppose that I would like to know whether I can map the state of the atom under this dynamics to a state which lies, let's say here, or here. How do I answer this question? Well, in this case, it's pretty simple, right? Because this is fully analytical. I could diagonalize, write down the unitary, and then solve this equation of motion. And then I will have some description for the state of this atom with respect to the time of the dynamics. And then I need to involve this along many different times. And then I could see the trajectory of this atom here, right? But then the thing is that, well, it might be that we start running, we have a very bad laptop. Let's but like this, and then this laptop is so bad that, well, we computed the trajectory up to here, we get some point here, we see what is the set of states, but we are a bit tired because basically this time can go up to infinity, and in order to know where this atom can end up, we have to keep iterating on time. So this means that we solve the equations of motion, and it's a bit frustrating because we really need to make this time very, very large to see all the possible states that you can achieve. And this is a very simple interaction. What happens if you have a very complex interaction, or I don't know, or that you don't even have a computer, that you have to compute by hand? It would be tragic. Well, actually, the framework that I presented today, so let me make one comment here. So this is what people call it by open dynamics approach. Well, open here in quotes, open dynamics approach. But then the framework that I derived today will answer this question that we wanted to know. What is the set of achievable states if we start with your atom here under this energy preserving unitary here without solving the dynamics? So basically the theory will be such that using minimal assumptions, I can get something like this. So same picture, but using this framework that I haven't defined yet, which is this resource theoretic approach. So what you get is that, well, the states of the atom, well, I mean, the set of achievable states, if we start at this state plus here, it's all this guy here that I depict. Well, it's symmetric, sorry for the drawing. But so this is the main motivation. So this framework that you develop will allow us to obtain this set of achievable states given some initial conditions without solving equation of motions. Well, I must be fair. The price that you pay here is that you'll be completely agnostic towards the microscopic variables that I might have to tune to, let's say, get here or there. So basically, this approach fails in a sense that sometimes we don't know how to construct this process, but sometimes we do. Okay? So is it more or less clear, or it's not so clear? Maybe one or two questions or no questions? Mm-hmm. It's a if and only if. Yeah. It's very nice. It's if and only if. But then, of course, okay, I will not give spoilers, but it's if and only if. Okay, great. So this is what we called by resource theoretic approach. And, well, and instead of telling you what is a resource theory, I will do this. I prefer to lay down what are the assumptions that I will use, discuss these assumptions and say, look, a resource theory is composed of 3 different objects, sets of free states, free operations, and monotones. But then I will avoid telling those things now, otherwise it can get very abstract and it's not, let's say, so pedagogical. So let me start then. But before, let me just erase this. By the way, a quick comment. I also prepare lecture notes, and so they look like this. Let me just show you. So basically, everything that I will attempt to say, it is written down in a nice and not sloppy way. And I mean, it's everything here, all the derivations, everything it's there, and then I will make it available. Maybe put in the website or on my GitHub. So if you don't want to take notes, there will be notes afterwards. Okay, great. So then the starting point is, how can we describe the thermodynamics of systems, which might be far or not from equilibrium, using minimal assumptions. Okay, great. So let's assume that we have a system which I will depict by this black dot. This system is characterized by some density operator rho and some Hamiltonian age. Okay, and then we will assume, and this is a big assumption, although it might not sound like, we will assume that this system interacts with a heat bath, and then the only constraint that I will put in this heat bath is that it is parameterized by some inverse temperature beta, 1 over T. We will make KB equal 1. And this environment here is prepared in a thermal Gibbs state. So I will denote it by gamma. Thermal states I will always denote by gamma. I will put an index of E, environment, and some Hamiltonian age E. And this gamma E here is simply E2 minus beta age E divided by the partition function, where the partition function is simply trace of E2 minus beta age E. Okay, good. Is the handwrite nice? Perfect. Okay, good. Why I said that this is a big assumption, that I'm assuming that the system interacts with this heat bath? Because we will assume that we will be always allowed to use this thermal bath to perform thermodynamic transformations. You can justify this in many different ways. You don't need to take this path, but up to this point, I will assume that I have certain control of this heat bath. So I can take my system, I can bring the bath, and allow them to interact. And as I said, I want to be the most general as possible. And the most general as possible for describing the interaction of system and bath is assuming that I have my system, I bring my bath, I assume that they are initially uncorrelated. It might not be the case, but I assume that they are, because we wanted to do some calculation, otherwise it gets very hard. And then the only assumption is that system plus bath form a closed system. We could follow an open quantum system approach that I mentioned in the last class, but this is the not most general way, because if I assume that I have certain control under the degrees of freedom of this bath, I can treat as a closed system, just like the Janice Cummings model that I wrote it here. So what does that mean? It means that they evolve under the action of some big unitary here. And this unitary is such that it conserves the total energy, meaning that it commutes with the local Hamiltonians. So this is called energy preserving condition. I will talk about this in a bit. Give me 1 second. Energy preserving condition. And since I'm interested in the behavior of the system, I will trace out the bath. And this defines what we called in the literature by thermal operations. Great. So basically here what I'm saying is the following. So I have the system, I bring the bath, I assume that this two subsystem lives in a shoebox. I'm just looking at the shoebox, and the energy inside of the shoebox is conserved. I'm not extracting energy nor injecting energy there. I'm taking into account all possible resources that I have, energetic resources. And this is, well, I will claim that it's the most general way of describing system-bath interaction. If I say, okay, but how about open dynamics? It's a sub-case of this, as I will mention in the third class. Great. Well, despite the simplicity of this is basically a CPTP map with two properties. So basically, I'm defining a CPTP map, which has two properties. But before this, let me put the references. This was Yazing, 2009, and Brandão and Oppenheim, 2014. And okay, so I said CPTP maps with two specific properties. Well, the first property is that this set of operation is time translation covariant. What does that mean? So it means that, I should write time translation covariant first. Time translation covariant. Well, this means that suppose that I have the suppose that I have the unitary evolution or the temporal evolution of my system, AGST, and basically what this property says to me is that, well, if I first evolve my system on time, and then apply my thermal operation, this is equivalent as applying the thermal operation first, and then later involving the system on time. Okay, simple as that. And this contains a lot of physics behind. Well, the first thing, which is non-trivial to say, is that basically what this tells us is that we cannot extract time-like advantage here, meaning that, like, look, I cannot manipulate time in such a way that I can make it better thermal operations. But this also means that this is also a manifestation of the first law of thermodynamics, because this comes directly from this energy preserving condition here. Okay? And a problem that I put is that just as an exercise, you can prove this. So basically, you take this dilation, you take this, and then you just check this if this works. Good. So this is somewhat like first law. And now the second property, which defines my thermal operation, is that this operation, this set, is Gibbs preserving. And this is really cool. What does that mean? It means that if I take, if this rho is a thermal state at the same inverse temperature as the BEV, but for arbitrarily Hamiltonians, so let's say that I take some gamma s with some Hamiltonian hs and apply my thermal operation, I get back this thermal state. So this is a fixed point of this map. And then this basically is, this encodes the second law of thermodynamics. Well, I need to define a measure, or I need to define a monotone to claim this, but up to this point, let's say that this encodes the second law of thermodynamics. Why? It's very simple to understand this physically, because imagine, like, I'm saying that we can always interact with this BEF, right? I can always take my system, takes this BEF, and apply this thermal operation. So this thermal operation is some sort of free operation that I can perform. Another way of looking at this is that this is basically some thermalization process, right? I can take the system BEF and then thermalize. But imagine if this operation here, imagine if this Gibbs state is not a fixed point. What we could do is the following. We could take a thermal state, apply a thermal operation, and map this initial state to some out of equilibrium state, out of equilibrium with respect to this inverse temperature beta here. So basically, I'm creating a thermality. And then, since I can always use this BEF, I take this system which is out of equilibrium, put in contact with the BEF, and what will happen now, the system will partially thermalize. And in doing so, we could extract work. I'm not defining work, I will do in the next, but basically this prevents us to construct a mobile perpetuum, basically. Okay, so far so good. Any question? Maybe objections or? So this guy here, just let me put here, can be any thermal state at some Hamiltonian hs. So by construction, I'm saying that this unitary commutes with the local Hamiltonians, right? So, but this, yeah. Thermal with respect to this inverse temperature. Yeah. So what we are doing is the following. Well, I will repeat myself in a slow way, and then I will try to give a more experimental example, okay? So here the idea is that, look, I have a system, and I have something that it can be very big or not big. The bath could be a qubit, right? Because I'm not restricting the size of this bath. My only restriction is that this bath is prepared in a thermal state. So what I'm doing is that I'm creating some map, defining this way that I have my system. I bring the bath. I assume that they are closed. I assume that I have some control under the degree of freedoms of this bath. I treat them closed. They evolve unitarily, and then I trace out the bath. Okay. So for example, I will talk about this in my third class. In those NMR experiments, for example, there's this very beautiful experiment that it was done in CBPF in Rio de Janeiro, where they took a molecule of I don't remember the name, is CHCl3, and then they dissolve this in acetone, and then they create a qubit out of it, and they treat the other as a thermal bath for your main system. And basically, they were engineering those energy-preserving interactions. So this would be a physical example of thermal operation, or the Jaynes-Cummings model that I started. Okay? Good? Perfect. So let me see, because I have this thing that if I start talking, I go much beyond what I wanted to say. Yes, so let me do something which for now it will sound weird, but we will use this later on, which is that one could think like, also answering your question, what is an example of thermal operation for instance? Well, an example, now you write here for you, is the dephasing map, for instance. The phasing map is a map that kills coherence in different energy eigenstates, right? So basically, a dephasing is simply this. So you sum over J, Ej, those are eigenstates of energy, Ej, rho, Ej, Ej. So this is a dephasing map. Dephasing map is a thermal operation, you can check. And basically, if you have a qubit, for example, with some population A, here, 1 minus A, some C, C star, what this happens is that if we apply this map, we kill the off-diagonal elements. Good. But what we can also do is to express the dephasing map as a time average, which is basically as a limit of tau go to infinity, 1 over tau, 0 tau, dt, hst, rho, hst. So this is an equivalent formulation of the dephasing map. So an exercise for you is to prove that you can, these two things are equivalent. But the reason why I wrote this is because basically, if we look at the energy preserving condition, what we can show is that the dephasing commutes with the thermal operation. So I can write like this. So what does it mean? It means that, well, if for some reason I would like to dephase, I could dephase first and apply my thermal operation. This has the same effect as applying the thermal operation and dephasing. I'm writing this because I will use to prove something later. Okay? But yeah, so in the notes, something that you can do for practicing is to try to prove these two properties and also show that you can write dephasing in that following way over there. And to do so, you just need to open up this guy here, right? You write explicitly what is rho, and then you do some algebra, you solve this integral, and then you can convince yourself that you have something very similar to this. Great. Well, thermal operations, as I will argue later on, might be hard to construct. So this also motivates us to define the notion of thermal process. So I will define as a thermal process. So a definition for us, I will define as a thermal process, like thermal process as any process satisfying property 1 and 2. So property 1, property 2. What does that mean? It means that this set is much bigger than thermal operations, right? So thermal process relaxes the fact that I might have that dilation over there. It might be that I have a map that satisfies property 1 and 2, but it might be that I cannot write it in that form over there. Great. And now, so as I said, so basically, I assume that I have a system, I have this path, I can always use this path. This defines the notion of thermal operations. Thermal operations is a free operation. Thermal states at that inverse temperature is a free state, and any other state which is not a thermal state at that inverse temperature, I will call it by resource. It's an out of equilibrium state. Why it's a resource? Because basically, if I apply a thermal operation, I can map this state to any other state which is not trivial. Trivial would be like thermal state. Then the question is like, okay, how can I quantify then this amount of resource that you are defining, this capability of being out of equilibrium, this athermality? Well, so you define a function called monotone. So basically, you define a function which acts on the space of states and maps you to real numbers, positive real numbers. And, let's put like this. And then you define a function with two properties. So the first property is that, well, if I take some state rho, I apply my thermal operation, and then I quantify the amount of resource that this state has. This is smaller or equal than what the system had initially. This kind of makes sense, right? Because I cannot, so by definition, thermal operations cannot increase your resource, so it has to be decreasing under this map. Well, the second property is that if I take a free state, so let's say that, well, a free state would be a thermal state, this should give me 0. So basically, monotones quantifies how much resource we have, how far from equilibrium we are, and we construct monotones in such a way that they respect these two properties here. Good. There are many different types of resource theories. Here I'm talking about thermodynamics, but we could think about other stuff, such as like, if we think about entanglement manipulation, for example, in this case, in this case, free operations could be local operations and classical communication. Separable states could be my free set. Or I could also define a resource theory for coherence, or with respect to a given basis. I could define a resource theory for, let's say, well, suppose that I'm in my lab and I only have linear optics instruments. I cannot generate non-Gaussian states, so I could also define a resource theory for non-Gaussianity, and so on and so forth, okay? So this is quite general. So, okay, good. So now the question is like, okay, can you give me an example of thermodynamic monotone that it will be relevant for us? And yes, I will just do it here. So a non-trivial and very nice example is simply the relative entropy of a given system rho with respect to a thermal state gamma. Why is that so? Well, let me open up this. So by definition, this is defined as the trace of rho log rho minus gamma. So this is just a definition of the relative entropy. There's 1 over beta here. So now we can up this in the following way, like this is simply the von Neumann entropy, right? Minus the von Neumann entropy. And then we have this minus 1 over beta trace of rho log gamma. Well, so this is equal to 1 minus beta S of rho minus 1 over beta. This is trace of rho log e2 minus beta h over z. Wait, yeah. I'm just doing some algebra. Yeah. So I'm using, yeah, the motivation is that after this line, you see that this gives rise to what is called non-equilibrium free energy. And non-equilibrium free energy gives you the maximum amount of work that you can extract from an out of equilibrium system. You'll see this in the next step. You could, in principle, you have many different monotones, right? So it does. So if you take this and this, you can, well, better. If you take this and put it here, you just need to use this inequality, this data processing inequality, and then you can get this, okay? Anyway, so let me finish this calculation. Let me see how. So I will do something. So I will, wait, no, not this one. I will write this as beta 2 minus 1. Is beta 2 minus 1 S of rho minus, well, look, so log of e2 minus beta h, it's simply minus 1 over beta plus trace of rho h, right? And then I have minus trace of rho log 1 over z. So this is minus 1 over beta log z. Okay, I just open up this. So this is simply, by definition, the average energy, E. I would just define as E of rho. And this term here, if we remember statistical mechanics, the canonical ensemble, this is the free energy of a thermal state. So this is minus F of gamma. Well, sorry for the confusion. I will write this. I will write this here. So basically, if I open up this quantity, what we get is that we have E minus rho. This guy doesn't exist. Minus 1 over beta S of rho minus F of gamma. Okay, let me erase everything now. Okay. So basically, if I take the relative entropy with respect to a thermal state, I can open up the equations, do some algebra, and arrive at this equation here. So this first term, it's an average energy. This is the von Neumann entropy, and this is the free energy of your thermal state. So this is a generalization of the concept of free energy for non-equilibrium states. Why? Because you have like some von Neumann entropy here. You have some average energy here. So this we simply denote by F, this beautiful F of rho minus F of gamma. And, well, and this is really nice, as I was telling Alberto that, well, Parondo in 2010 proved that, well, the maximum amount of work that you can extract from a system out of equilibrium is given by this quantity here, the non-equilibrium free energy. And it kind of makes sense, right? Because look, if we think about classical thermodynamics of transformations of systems which are in contact with a thermal bath at temperature beta or T, the maximum amount of work that you can extract is bounded by the equilibrium free energy, right? And here we have a generalization for when this guy is out of equilibrium. Observe that if I start with a thermal state, then this goes to 0, meaning that I cannot extract work from, well, my system is not out of equilibrium. Okay, so how are we doing? Is it okay? Yeah? So, yeah, so for this class, I don't need this, to be honest. I think it's nice because this makes a nice connection with classical thermodynamics, and this also allows us to look again to this Gibbs preserving thing and then connect with the second law. And then basically, just to summarize everything, thermal operations defined as that dilation over there is CPTP maps with these two properties here. And these two properties is precisely first and second law of thermodynamics. And as I said, we relax to the condition that, well, we will look at thermal process as process which satisfies properties 1 and 2, and we will not care so much if we can write that dilation explicitly there. Good? Well, now I pose the question that I would like to answer in this lecture notes. So it is 2 questions. And the first question, Q1, is like the question that I would like to answer in this series of 3 lectures is, given a thermal bath at some inverse temperature beta and a pair of states rho and sigma, I would like to derive the necessary and sufficient conditions to say whether there exists a thermal operation that I can map rho into sigma. I want to answer this question. And answering this question, which we will see it's not so easy, will allow me to answer a bigger one, which is, again, given beta and rho, what is the set of states that we can achieve under thermal operations. Yeah, good. Great. And in order to answer this question, I will define this notion of thermal cones. Let me see. I will erase the less important part. Yes, this I will leave it here. So let's make a def of definition. This idea of thermal cones. So the idea of thermal cones is the following. So imagine that you have our initial state rho, and we have access to this thermal bath. What I would like to characterize is the set of states achievable from rho. So I will draw like this. So the sets, you like this, and then I will denote like this. So the set of states that I can achieve from rho, I will call this by future thermal cone. Right? And basically, future thermal cone is any state sigma here that if I apply my thermal operation on rho, I can get it. Okay? Good. Well, to make things more interesting, I could also define the past thermal cone as the set of states that can achieve my initial state rho. This pass thermal cone. Good. So this is my pass thermal cone. And now it comes one of the most beautiful results in quantum thermodynamics, which is the fact that when I look at finite size systems, I have finite size effects. What does that mean? It means that I don't have a single second law, but I have a family of second laws. So this order is not total, but partial. So this means that there exists a set of states which is neither in the past nor in the future, but they are here. And this set is called incomparable. And okay, so yes? Yeah, that's true, yeah. You got me on this, yeah. So no, yeah, I'm assuming that I have a finite size system of dimension D. And yeah, so this is a good point. I have a finite dimension system of dimension D, and I can close this partial order to a total order if I add one specific element there, which is called correlated catalysis, which gives you like this infinite dimension thing and then allows you to recover classical results of thermodynamics. In the system. I will be completely agnostic towards the Beth. How are we with time? That's good. Okay, great. So I would like to characterize those sets, like the set of states that I can achieve under thermal operations, the set of states that can achieve my initial state under thermal operation, and the set of states that neither live in the past nor in the future of this initial state. Well, unfortunately, we will not be able to characterize this in full generality, and this is very sad. We have a characterization, complete characterization for qubits, but for general quantum states, we don't have it. It's an open problem. But we can focus on a specific family of states, and we can provide a very clear and nice answer. And it's nice because the answer of this kind that connects with the two previous classes. And I will tell you why when I present those results. But now, let's look at this family of states then that we can answer this question. So let me see where to write. So I want to keep this. I will erase thermal operations. While I do this, how is it going? Is it clear or are you guys following? Yeah? Good. So great. So we restrict ourselves to energy incoherent states. So those states are those which are diagonal in the energy eigenbasis. So what do I mean is that I can take rho as sum over I, sum pi, ei, ei. And this, I assume that my system has dimension D. So it's energy incoherent states. And when I restrict to this set of states, what I can do is that, well, I could look at those probabilities which appears here because the trace is 1, then this will sum to 1. And instead we can describe the system in terms of a probability vector, which goes from P1 to PD. Okay? So this guy lives in the probability simplex. It is the space of states in this case. Okay? Why I'm doing this? Well, first, the honest question is because we know how to answer this question. And by doing so, we have a very beautiful theorem which says, this theorem is also by Brandão, 2013, and Michał Horodecki. And then basically what this theorem says is, well, there exists a thermal operation mapping rho into sigma if and only if there exists a stochastic matrix mapping P into Q. P are the eigenvalues of rho, or simply the populations of rho. By the way, I will call those probability vectors as populations, and Q is the eigenvalues or the populations of sigma. So basically what this theorem tells us is that there exists a thermal operation mapping rho into sigma if and only if there exists a stochastic matrix mapping P into Q. And this stochastic matrix is Gibbs preserving. Well, a stochastic matrix, it's a matrix where all components, you just write like this, are greater or equal to 0, and the columns sums to 1 by probability conservation. And if you remember, a stochastic matrix describes the most general way of probabilities evolving. Okay, there's a lot of nice physics on this. So let me pause a bit and discuss a bit more, because this really gives us a direction to answer that 2 questions there. Why? Well, first, because thermal operations tells me I take my system, I bring a bath, I allow any energy preserving unitary, and this defines my map, and this map has to satisfy those 2 properties that I was saying. So if I want to know whether rho can be mapped into sigma in that picture, basically I would have to check for all possible thermal baths, all possible energy preserving unitaries, right? And this problem is untractable. Moreover, what is very interesting here is that, well, we start with density operators evolving under CPTP maps. We found equivalence of probability vectors evolving under stochastic process. And this is much more simple. Why? Because this problem is classical. Then the question is, what is quantum then in your theory? I will talk about this in the 3rd class. I see that I have been promising a lot in the 3rd class, no? But yes, so how can we prove this? Well, as I said in the very beginning, easy results I will prove, hard ones I will write it in the notes. And this direction, it's very easy to prove, and the other direction is a bit hard, but it's doable. Well, basically here, the idea is the following. So let's assume that we have a thermal operation mapping rho into sigma. And now we can use that, okay, I erased. We can use the fact that I wrote here that the phasing commutes with thermal operations, right? So basically, what I can do here is that, well, I could dephase both guys. And so if I dephase both guys, I kill coherences. So I'm looking at populations, right? And I would just take one matrix element to make it simple for me. So basically, let's say that I take EK. Okay, this is sigma, sorry. This is, let's say that this is QK. So I have QK equal. And now what I can do is that I have my dephasing here. Well, I can swap, sorry. I can use the fact that dephasing commutes with thermal operation and write this as E of dephasing of rho. And now I can write this as rho of J rho of J, J, J. Like this, okay? So what I did was, I simply used this equation of the dephasing operation here. And since I can commute things, I just swap these two guys. So I have PJ here and the dephasing here, okay? And now you can define this to be some guy like this. And then as an exercise, you can prove that this is a stochastic matrix. So proving this direction that if there exists a thermal operation mapping rho into sigma is if and only if there exists a stochastic matrix which is Gibbs preserving mapping P into Q. In this direction, the proof is just here. It seems a bit blind. You have to open up and you just need to do some algebra to convince yourself that this is a stochastic matrix. It's in the notes. Sorry? So why dephasing? So, well, because basically we want to look at populations, right? So, and I knew that, well, if I dephase this guy, I have my vector Q. And if I dephase this guy, I have my vector P. And by doing this, I get this equation. And this is just a stochastic matrix. Sorry? Sigma could be any state, yeah. So, well, here I'm restricting myself to energy incoherent states, right? And I dephase just to show that this direction implies this thing that I'm writing. Well, yes, if the dephasing commutes with your set of operations that you allow, then it's true. But the fact that the dephasing commutes with Hamiltonian, that the dephasing commutes with thermal operation, it's not, well, it's trivial now that we look at the definition, and the fact that this is a stochastic matrix, not sure if it is that trivial. But if it's trivial, it is good, right? Because at least now we have a way of answering more or less a path to answer the first question. Well, to prove the other way around, what you can do is to construct a thermal operation. And to prove the other way around, basically what you do is the following. Since thermal operations are energy preserving, so this means that you can decompose this thermal operation into blocks which acts on the generated energy subspaces. And then if you construct a bath which has a big degeneracy, you can move things around, you can permute things around, and then you can prove. But it's not trivial. Like this direction it's quite hard. So this is why I will not prove. Great. So basically, so let's forget this proof for a while. So basically, the idea is the following. If I want to know whether there exists a thermal operation mapping rho into sigma, then this boils down to try to find a stochastic matrix which maps P into Q and preserves the Gibbs state. This is the claim. Good. But notice that I still didn't answer the question 1, right? Given a bath, whether there exists a thermal operation mapping rho into sigma and how I can characterize this set. What are the necessary and sufficient conditions for doing this? And okay, so how many minutes I have? 20. How much energy do you guys have? Yeah. Because I could either, because basically what I'm gonna do now is I will look at an extreme case where I can provide an answer for this question. In the case that the temperature of this bath is infinity, then I will resort to some mathematical theorems and then answer this. But then this also requires some discussion. So either I could do this or I could simply stop here and then I can stay here and then you guys come and then we have a chat. And then tomorrow I can start from this part because this is what I was planning. So yeah, so maybe we can finish for here. But I will be here, huh? Okay.